Hi again. Before watching this video, please make sure you have viewed the video on mole concept. In this video, I will show you how to determine empirical and molecular formulas. I will show you how to do empirical formulas from known masses and from percent composition and by indirect means. And I will show you how to figure out the molecular formula from the molecular masses. If you consider a compound, say C6H6, what this means is that this compound was made up of 6 moles of carbon combined with 6 moles of hydrogen. Now the fact is that you cannot really measure moles of carbon or moles of hydrogen in the lab. What we can measure is the mass of carbon and the mass of hydrogen. And once we know the mass of carbon and mass of hydrogen that combined to make your hydrocarbon or the new molecule, you can go from mass to moles for each of the elements. And once you've figured out the number of moles, you need to figure out the lowest whole number ratio. If X and Y turns out to be some decimal number, then we have to do some basic math and convert the mole numbers into the lowest whole number ratio. And that's what makes the empirical formula. Now, to find the molecular formula, you will need to know the molar mass. Let's begin by doing some exercises. From masses. Elemental analysis of a sample from ionic compound gave 2.82 grams of sodium, 4.35 grams of chlorine, and 7.83 grams of oxygen. What is the empirical formula? The first thing we want to do is make a list of the elements involved. We have sodium, we have chlorine, and we have oxygen. In the next column, you want to write down the masses. You have 2.82 grams of sodium. Make sure all the mass units are in grams. 4.35 grams and 7.83 grams. Then you want to calculate the number of moles of each. So going from mass to moles, you will be multiplying by 1 mole over the atomic mass unit. We can get the atomic mass unit from the periodic table. So for example, for sodium, it is 23. So 2.82 divided by 23 gives you 0.1226. So we have 0.1226 of moles of sodium in 2.82 grams. Similarly with chlorine, the atomic mass unit is 35.453. So if you multiply by 1 over 35.453, you will get 0.1227 moles of chlorine in 4.35 grams of chlorine. And for oxygen, you want to multiply by 1 over 16. And 7.83 divided by 16 will give you 0.489. So you have 0.1226 moles of sodium, 0.1227 moles of chlorine, and 0.489 moles of oxygen. To get the empirical formula, we want it to be in the lowest whole number ratio. Okay, so to get to the lowest whole number, you look at the list of the number of moles, pick the smallest number, and divide each one by the smallest number. So let's go ahead and do that. So this will be close to 1, and chlorine would be close to 1, and 0.489 divided by 0.1226 will be 4. So your empirical formula would be 1 sodium, and you don't have to write a 1, 1 chlorine, and you don't have to write a 1, and 4 oxygen. And that's your final answer. Now let's go ahead and see how to get the empirical formula from percent composition. Ascorbic acid, vitamin C, contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. What is the empirical formula? So since we have percents and we need to convert percents to grams, the best thing to do is to make an assumption. You want to assume that your sample is 100 grams. So 40.92% of 100 is 40.92 grams. So when you make your list of elements here, and you have your mass, and you have your moles, carbon will simply be 40.92 grams. Similarly, hydrogen will be simply 4.58 grams, and oxygen will be 54.50 grams. And then converting it to moles, you simply want to divide by molar mass or atomic mass. Let's just use 1 here, and let's use 16 here. So 40.92 divided by 12.01 gives me 3.407. So you have 3.407 moles of carbon in 100 grams of sample. You have 4.575 if you multiplied it by 0.001, 0.575 moles, and this one would be 3.406 moles. Okay, now we need to convert it to whole numbers. And the trick is to find the smallest number in this list and divide each one by the smallest number. So if I did that, I got 1, 1.3, and 1. And since I cannot have any decimal, I will multiply every single one by 3 so that I get a whole number here. So I get a 3, 4, and 3. Okay, so the rounded numbers are 3, 4, and 3. From here I deduce that the empirical formula is C3H4O3. This next problem is very interesting. The information given here is completely different from what we have been given before. Vitamin C, molar mass of 176.12 grams per mole, is a compound of carbon, hydrogen, and oxygen found in many natural sources, especially citrus fruits. When 1.000 grams of sample of vitamin C is placed in a combustion chamber, I'd like to pause and tell you what combustion is. When you take a compound and when you put it in a combustion chamber, you must automatically add oxygen, and the product is automatically carbon dioxide and water. That's a type of reaction, it's called a combustion reaction, that occurs particularly with compounds that contain carbons and hydrogens. All right, continuing on. And burned. The following data was obtained. The mass of the carbon absorber after combustion was 85.35, and the mass of the carbon dioxide absorber before combustion was 83.85. So the mass of carbon dioxide must be 85.35 minus 83.85. Mass of carbon dioxide is 1.5 grams. So let's just put down 1.5 here. Reading on, the mass of the water absorber after combustion is 37.96. Mass of the water absorber before combustion is 37.55. So what is the mass of the water equals? So this was 1.5 grams. 37.96 minus 37.55 gives us 0.410. So the water is 0.410. Okay, at this point, we want to make our list of elements here, which is carbon, hydrogen, and oxygen. And we do want to figure out the mass of the elements in this little box here. So we have carbon, hydrogen, and oxygen here. Okay, What we do know is that this is 1.000 grams of compound. We really don't know how much carbon, how much oxygen, and how much hydrogen we have here. But what we do know is the portion of carbon dioxide that comprises of carbon. The law of conservation of mass will tell you that if you take an unknown compound which contains carbon, all of the carbon will be converted into the product containing the carbon. So we know that carbon dioxide is the only compound that contains carbon. So whatever carbon was in here converted to the carbon in here. So if we could figure out the mass of the carbon in the carbon dioxide, we'll know the mass of the carbon in the original compound, and we'll be able to put a number here. If you consulted your periodic table, just rounding it up a little bit, for carbon dioxide, the part of carbon over complete carbon dioxide is 12 over 44. So 12/44 is the portion of carbon. If you're wondering where I got 44 from, the molar mass of carbon is 12. The molar mass of oxygen is 16. 16 times 2 is 32. And if you combine them, you do get 44. So what is 12/44 of 1.5? If you picked up your calculator and figured that out, you will get 0.409. So carbon is 0.409 grams in carbon dioxide, and hence in the original compound. So we got the mass of the carbon in the original compound. Similarly with water, look at the hydrogen. The only place where you see hydrogen is in water. If the original compound had hydrogen, it was combusted completely. All the hydrogen in the original compound went on to make water because of the law of conservation of mass. So hydrogen is 2, there's 2 hydrogen, and 16, this is oxygen is 16 and the hydrogen is 2, so 16 plus 2 is 18. 2/18 of this entire water molecule is comprised of hydrogen. So 2/18 of 0.410 is what? So that would be the hydrogen, the mass of the hydrogen. So 2/18 of 0.410 is 0.0456 grams. Okay, we are told that the original compound has oxygen. From the word combustion, you know to add oxygen in the reactant side. So, and there's oxygen present in carbon dioxide and oxygen present in water. It's very difficult to tell where the oxygen went. So we do not have a method for figuring out oxygen like we did for carbon and hydrogen. But luckily, we know the total mass of the compound. So if you added these two mass, take it away from 1, that will give you the mass of the oxygen. So I'd like you to pause the video and do that little math for me. So did you get 0.545? And now you can pause the video and figure out the number of moles for each one. Okay, so let's see, what was your number of moles for carbon? 0.409 divided by 12.01 would give you approximately 0.034. 0.0456 divided by approximately 1.008 would give you 0.0453, and 0.545 divided by 16 would give you 0.0341. So going through this whole scenario again, the word combustion tells us that that unknown compound that contains carbon, hydrogen, and oxygen combined with oxygen to produce carbon dioxide and water. All of the carbon in the original compound ended up in carbon dioxide. And you know that the portion of the carbon in carbon dioxide is 12/44 from your molar mass. If you looked at the periodic table, carbon is 12. carbon dioxide added up, 12 plus 32, oxygen being 16, is 44. So the portion of carbon is 12/44. And since you know from the experimental data that 1.5 grams, 12/44 of 1.5 gives you 0.409, and from mass you can go to number of moles. You did the same thing with hydrogen, where hydrogen was 2/18 in water molecule. The hydrogen was 2/18, and all of the hydrogen in the original compound ended up in water. So you could very accurately determine the portion of the hydrogen multiplied by the mass of the water, 0.41, gives you the mass of the hydrogen in the water. That is also the mass of the hydrogen in the original compound before the combustion. Converting this to number of moles, you get 0.0453. You did not determine this oxygen in the same way. You simply added these two numbers and subtracted from the total mass of the sample. And that's where you got 0.545 divided by 16 gave you 0.0341. Okay, we're almost there. All we need to do is convert it to the lowest whole number. And look down the list of number of moles and pick the smallest number and divide each one by the very smallest number. So you get 1, 1.3, and 1. And then you need to deal with 1.3, and multiplying by 3 takes care of that. And we have 3 carbon, 4 hydrogen, and 3 oxygen. It's the same compound as the previous problem, but a completely different set of data. In the previous problem, you were given the masses. It was very easy. In this problem, you were given some experimental data. This is determining the empirical formula by indirect means. I now want to tell you how to do the molecular formula. Notice that the molar mass of the compound is given as 176.12. If you determine the molar mass of C3H4O3, you will discover that that's not the molar mass of the compound given. I'm just going to round here a little bit. 4 times 1 is 4, and 3 times 16, this is for the oxygen, this is for the carbon, and this is for the hydrogen, is 48. And what you do get is you get 88 grams per mole. You don't want 88, you want that for the molecular formula, because the molecular formula must match the molecular mass or the molar mass. Okay, so what we need to do is we need to keep 176.12 in mind. Ask ourselves, what do we have to do to this number to get to 176? You're allowed to round a little bit, so this is almost double. Because the molar mass is almost twice the molar mass of the empirical formula, the molecular formula, it will be double the number of moles. So C6H8O6 is the molecular formula. Alright, great. This ends this video. I know we've covered a lot, and the only way you can grasp the concepts that I've covered in both the mole concept video and in this video determining the empirical formula and the molecular formula is to actually rerun the video, pause the video, and see if you can do the problems on your own, and then run the video to check the answers. Thank you very much for listening. Goodbye.